Okay, welcome back to part 2 of the lesson, talking about statistical techniques, specifically about standard deviation and the mean of the population. But finding standard deviation and mean of the population can be very difficult, because if we're talking about an entire population, it usually means a lot of different numbers. So this is where sampling comes into play, and sampling becomes important. Taking a good, valid, random, simple sample, and then being able to calculate the standard deviation and the mean of the sample. And as long as we've got a good sample, as long as we've got a good, random, simple sample, then we can apply the mean and standard deviation of the sample to the entire population. There is one slight difference in the calculation. One thing is a little bit different. So we're going to go through another example here. I'm going to talk about Basal's correction, or that's what it's called that we do. It's a little bit different. I'll explain that in a moment. And I want to do this one but longhand. We're going to do this one. Obviously, everything will be done on the calculator, but we're going to actually do this one out longhand with all the work and with all the calculations along the way. Actually, you know what? Before I get started, by now the last chapter tests should be entered in the grade book, so you will have a chance to do test corrections this Thursday, which is the math advisory period, and this Thursday will be the 5th, and we're just going to do part 1. Test corrections on just part 1. You'll have 30 minutes. Now, I will, Thursday morning, I will put a note in Synergy saying that you can come directly to class. So after your first hour class on Thursday, come directly to my class, and you'll be able to get your tests. Again, just part 1 of the test, and do corrections. Corrections are open notes. You can use your calculator. You have to work by yourself. You can use your textbook to help you out as well. By now, I'm sure a lot of you realize that many of the questions actually came right out of the textbook. You're going to do corrections on a separate piece of paper. And you're going to staple it to the front of the test and then turn it back in. And then after that, you can just kind of stay after the advisory period and stay straight into into our second hour class that day. So that'll be this Thursday. And then next Thursday, you'll have a chance to do corrections to part 2 of the test. All right, so let's talk about these the Basal corrections now. So we know the population mean. Does it seem a little dark? Do I have my light on? Let me turn the light on, see if that's a little bit better. Take a little while for it to adjust there. The population mean is the X bar, but what about if we want to talk about a sample mean? Again, the sample has to be a good, valid, reliable sample, and as long as we've got a good, reliable, valid sample, then we can do the sample mean, and we use mu for the sample mean, the Greek letter mu, for good, unbiased population. And we can also do standard deviation of our sample. And again, all of these things can be done on the calculator. There is one slight difference that I want to talk about. The mean is going to be the same. For the sample, you're just going to add up all the numbers, divide by how many there are. There's not going to be any difference there. But for a sample standard deviation, we do something called Basal's correction. And the idea is that now my sample, my standard deviation for my sample is going to be the standard deviation of n minus 1. And here comes the scary calculus part. It's still going to be the sum from I equals 1 to n of the mean minus, or the data point minus the sample's mean squared all over n minus 1. So we have one less here. By dividing by a sample size of lowered by 1, Basal suggested that we compensate for the fact that we're working only with the sample rather than the whole population. So if you have a sample and you want to make predictions about the population, then we can use the mean and the Basal's correction for standard deviation. Let's look at an example, and this time we're going to do everything by hand. We're going to do it all by hand calculations here. So, suppose we work in a factory that makes thumbtacks. And we make the thumbtacks, and the thumbtacks have to be a certain size. They have to be a certain length in our thumbtack. We have our little thumbtack here, and we're very interested about the length of the thumbtack. If the lengths are too short, then the thumbtacks are not going to be very effective. They're not going to stick in where they want. Our customers are going to get frustrated. They're going to stop buying our inferior product. If the thumbtacks are too long, that might equally be problematic. Plus, if they're too long, it's costing us a lot more money in raw materials. So we're very interested about this. But in our factory, we might be making thousands and thousands of thumbtacks every day. So let's say we're going to make them in batches of 1,000 thumbtacks. So every batch that comes off is 1,000 thumbtacks. And we might be making, 50 batches a day. And what we're going to do is we're going to take a sample of those 1,000 thumbtacks. Remember all the different ways that we can take a sample. Maybe we could pick a certain number, start with a certain number, and then do start with the 273rd thumbtack, and then do every 91st thumbtack after that. Or we might want to do, I don't know, however we want to do that. But we're going to take a sample, and to make it relatively easy, we're not going to do take a whole bunch of points here. What we're going to do is we're going to just take a sample of 8 thumbtacks. And I want this to be a good, reliable, valid sample of 8 thumbtacks. And then we can find the mean and the standard deviation of my sample. And because it's a good, valid, random sample, we can apply that to the whole batch of 1,000. And if the sample's good and the sample's okay, then we say, oh, these 1,000, they're okay. That's all right. But if there's a problem with the sample, there are too long, too short, or whatever, I've got too many outliers, then maybe we need to destroy that 1,000, that batch, put them back into the melting pot and do it again. Or retool our machines, or do something different. Something's going wrong if that sample's there. All right, so here we go. So let's say that everything's valid, everything's good. So here come our sample. We're going to pull the random 8, and this is what we get. We find out that we get thumbtacks with the following lengths. The first one is 1.0 centimeters, and then 1.1 centimeters, 1.0 centimeters, 0.8 centimeters, 1.4 centimeters, 1.3 centimeters, 0.9 centimeters, and 1.1 centimeters. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Those are my 8 samples there. And let's say that we want them to be exactly 1 centimeter long. That's our desired. So we can see that we've got ones that are as short as 0.8 and as long as 1.4. Is that more than, is that an outlier? Is that more than 1.5 interquartile ranges from the median? I mean, what's going on with our sample? How valid is all of this? So this becomes our data. So So now, normally we would just plug this into our calculator, hit a couple of buttons, and let the calculator do all the work for us. But this time we're going to do everything by hand. Everything by hand. So we're going to create a table. Here's what our table is going to look like. So on our table, we're going to have our data point, and we don't have to put them in any particular order. So 1.0, 1.1, 1.0, 0.8, 1.4, 1.3, 0.9, and 1.1. So here's my data table. Now what I'm going to do is I need to find, well, what is the mean of all of those? I need to add them all up and divide by 8. So I'm going to use my calculator to find the mean. All right, so 1 plus 1.1 plus 1 plus 0.8 plus 1.4 plus 1.3 plus 0.9 plus 1.1. I get 8.6 divided by 8, and I get 1.075. So my mean is 1.075. Now that's going to be the same. That's the same here. In the next column, what I want to do is I want to find the difference of these. So I'm going to take my data point minus the mean. So this minus that. So the data point minus the mean, 1 minus 1.075, is going to be 0.075. 1.1 minus, see, we're going to get some negatives here. If we want to check them, make sure we're right on the calculator. 1 minus 1.075. Wait, did I do that right? 1 minus 1.075, negative 0.075. 1.1 minus 1.075. And I get 0.025. Notice that some of them are going to be positive, some of them are going to be negative. Here, negative 0.075, 0.8 minus 1.075, negative 0.275, 1.4 minus 1.075 is 0.325. 1.3 minus 1.075, 0.225, 0.9 minus 1.075 is negative 0.175, and then finally 1.1 minus 1.075 gives me 0.025. If I took a look at all these numbers and added them up, I should get 0 here. In the next column, what I'm going to do is I'm going to take that value and I'm going to square it. Whatever this value is, I'm going to square it for the next column. So, negative 0.075 squared gives me, oh, look what I did. Did you see that? I put the negative out there. It gave me a negative here because I didn't put it in parentheses. All of these numbers are going to be positive, aren't they? So be careful. They should all be positive numbers here. So I'm going to get 0.005625. And then if I subtract these, I should get 0.025 squared. Oh, I'm getting a scientific notation, but that should be 0.000625. and then this should be the same 0.005625, and then 0.275 squared. Let me make sure everything's on the calculator here. And then I'm getting 0.075625, 0.325 squared, 0.105625, 0.225 squared, 0.050625, 0.175 squared, and I'm getting 0.030625, and then 0.025 squared. Again, that scientific notation, 0.000625. And then what I want to do with this, did you remember from the formula? What does the formula say? Where did that sheet go with the formula? Remember, part of the formula says it's the sum of all of the differences squared. So the mean minus, the data point minus the mean, here it is, squared. And here it is. I want to sum all of these up. I want to add up all of those numbers there to save us a little bit of time. I'm going to tell you that if I add up all of these numbers, I'm going to get 0.275 if I add up all of these numbers. So this is the sum here. Now I'm going to plug it into the formula. That's the magic number. This is the whole reason we're making the table, is to find that number right there. Now, substituting into the formula, remember the formula said that the standard deviation for my sample is going to be the square root of the sum from I equals 1 to n of all the data points minus the means squared over n minus 1. So it's going to be the sum of, this is the whole reason for the table, that's going to be the 0.275 divided by, and because we're dealing with a sample now, we're not going to deal with 8, it's going to be 8 minus 1 here. So 8 minus 1. The square root of 0.275 over 7. On the calculator, I'm going to do the square root of 0.275 divided by 7, and I'm getting approximately 0.1982. So that's my standard deviation. There it is. That is my standard deviation. My standard deviation of the sample is 0.19882. And then I can decide, well, is that too big? Is that too small? What about those numbers that were the really big numbers, or the really small numbers? Are they outliers? Do I need to destroy this batch? Is this too big of a standard deviation? You know, is it too much of a range? Is it acceptable? I mean, what is my limit? You know, what do I want my sample to be? And kind of make my decision based on that. All right, so there it is by hand. And certainly this isn't something we would want to do if we had data points that were in the hundreds of data points. Certainly wouldn't want to make that table for something that large. But just making the table, that's how it works. I mean, if you did the data table, it would work for the entire population too. You wouldn't have to use Basal's calculation. You could just actually do it by divided by n. All right, so I think that's everything we need to know. So now go ahead and do homework 5G. And you've got a couple in there that you're going to have to do calculations in there, and looking at standard deviations and finding means, and it becomes quite tedious. Doing all the calculations, adding it all up, making the table is the way of showing the work. That's the work, and finding that magic number, adding up all the sum of all of the differences of the squares. That's the big difference there. All right, so on Thursday when we come back, you'll have a chance to do corrections, remember, on the test, and then we will talk about frequencies. Cumulative frequencies is our next lesson. So we'll see that one coming up, and I will talk to you again on Thursday. Bye.